photos because then I cannot see your faces by the presentation. I will try to do it here in this way. I made a little presentation about how to implement lasers in thick plate area and which area do I think? So where the laser already is in production. It's a crane building for butt joint up to 8 millimeter plate thickness for S1300. Shipbuilding, butt joint, 80% of the plates are between 6 and 10 millimeter. That's important to know. And also shipbuilding, the T-joint, 80% of the plates between 6 and 10 millimeter. On the left side, you can see the panel machine of Meyer Werft. They are working with hybrid welding because of deviation and other things like good mechanical properties. And on the right side, there is a Kranausleger. So it's a telescope, one part of the telescope of the crane for a mobile crane. And this is longitudinal welded with a laser beam. And this is around about 4 millimeter thick. So this is state of production. There are some other things maybe, but this is the thing which is done with the laser in the thick plate area. The things I dream of, this is pipe welding, longitudinal weld as a butt joint up to 100 millimeter plate thickness. Wind energy towers, also longitudinal welds as a butt weld up to 100 millimeter plate thickness, and the circumferential weld as a butt joint. And what I think of, and I hope to do in an European Union project, is to weld these very big pipes. So this is my colleague Michael Clemens, and this is me. And we are at Civan, and we hope to make the longitudinal weld. Do you see my mouse?
Yeah.
Okay, that is this weld here, and it is a can made in 4 different or with 4 different plates. 1, 2 plates, 3 plates, 4 plates, and the height is, or the diameter is 9 meter. And this, and this is what we plan to do. And unsuitable applications in the thick plate area. These are applications requiring work in different welding positions, especially overhead positions. So we made that. We succeed one time, and for the second weld, we damaged a complete machine.
Oh.
Yeah. So it was a pipe where we tried to go around with a robot from all sides, and in the overhead position we got problems. And this, so for laser beam welding, I think overhead position, no, it's not a good choice. But maybe you can try it and you can destroy your machines. But yeah, overhead position is not so easy. And one thing is applications with varying gaps. I will not say that it is not possible to bridge the gaps. But if you have a gap between 0 and 2 millimeter, then you have to adapt the process. I will come later to that. And then it is much more difficult to control the root and the melt in the thick plate area. And maybe it is possible. Maybe we find the right shapes for that. But what you need in each time, if you want to weld gaps, you need additional film material. And the question you have to ask always is, what can we do better than with a normal fiber laser? Where or how can I use the shapes I have, or the different shapes I can use to make things better than with a standard fiber laser? This is a big question.
Yeah.
And if you plan to do gaps, to bridge gaps, then so can we make a very small break, only for 1 minute? I will change my room. Okay, I will back in 1 minute. Okay.
Yeah, of course, no problem.
Yeah. I hope that my internet will not interrupt. So. Sorry? So I was in the kitchen. I'm at home. I told you yesterday why. Okay. So the connection is already okay. Great. So varying gaps, I think that is really critical. And the question is how we can do it better with shapes and so on. And if we have gaps, then we need filler material. And then is the question, can we do it better with filler material or with a hybrid welding process by using Civan lasers? So and now to a few requirements or some thoughts I made in the last days. All areas in which human life is at risk or the environment is endangered due to a failure of the machine. If you have a wind energy plant which breaks, then someone will be dead. Component or constructions are known as regulated areas. So the big exception is automotive industry. And there you need special requirements applied to manufacturing and for laser beam welding. And this is the ISO 15614 part 11 specification. And you talked about it. You have certificate some welds according this standard.
Yeah, we are familiar with this one.
Yeah, genau. So, and this standard refers to other standards. It's the 1569 part 4. It's a specification and qualification of welding procedures. You have done it. And the Bible for every for every laser beam welder is the 13919 part 1 and part 2. And both I made the last revision in 2019 and 2021.
Ah,
So I am
cool.
very familiar with this standard. Yeah, coming now to what I talked about the route. And for me, it is the most important thing. Normally, you can see this route here, this dropping out. You have solved this problem, concrete, yeah. But for my understanding, your route should look like this one, not the completely. Unfortunately, so these are routes made with your laser, but we had some trouble with focus shift. I think we are on the way to solve this. So longer wells, it was not possible for us to make good routes here. It's an 8 millimeter thick plate, but you can see if you are able to do such routes here, then this is the standard where I can say these routes the customer wants to see.
Okay.
Another thing, this slide or this picture is from my friend Michael Redmeier in Berlin from the BAM. He has a 60 kilowatt Trumpf disc laser. I don't know why, but now he has such a horrible thing in his lab. And you can see that it is not possible for this laser to get a higher penetration with the laser or laser hybrid by using more power. So you can see for 30 kilowatts, it's okay. 35, 40, it's okay. And beginning with 45 kilowatts, there is no deeper penetration, but the weld gets wider. We know the reason for that. It's the plasma above, or it's not a plasma, it's a plume.
Yeah.
It gets hotter and hotter, and you have a scattering of the beam, and a scattering, if you do it with your Civan laser, then the shape will destroy it, I think. So we are working on this topic together with Stuttgart. Maybe Christian Hagenlocher had informed you. If not, so we are working on this topic with them together in a DFG proposal. If it is time, we can show you the latest results, but this I don't want to do without Christian, because these results are from him, from his institute, and not from my institute. And yeah, that's it. So and this is the problem. You cannot get deeper at the moment, and looking to the industry in the thick plate application, they are very conservative, and they often use a submerged arc process. And this process is pore-free, notch-free, and yeah, it's fantastic. Best, excellent mechanical technical properties. You can you can increase the toughness by using different flux wire combinations and so on. So and it's well known. It was found, I think, in the 1920s in the Russia area. So really a good process, but high energy consumption and also very slow and expensive. But if you want to convince industry in the thick plate area, which are very conservative and use submerged arc process, then you need quality level B or better.
Yeah.
So you have the certificates, congrats again, but I think this is not enough for these applications.
Yeah. I agree with you. Yeah, we feel
Okay.
it from the customers, I think, that we certified it, but it's
Yeah,
still not enough.
no, it's not good enough. And I think the reason for that is the root. But for that we can, I will show you another opportunity what you can do.
Okay.
The question always is, what can you do better with the shapes in comparison with the other laser suppliers? And something must be better with your laser in the thick plate area than with the fiber laser. And there are some things. Maybe so for mild steel, you need better Sharpies, I would say. So the toughness is a thing where we can think about it, that we can influence it. The hardness itself, I think, in the heat affected zone, you cannot change the hardness because you always weld between 0.8 and 1 meter per minute. And what you do with the shape, it will not influence the heat affected zone. It will influence the melt and maybe the solidification, but not the heat affected zone. And this is a fact. So if you do mild steel, then you need the right T85 time. That is the time between 800 and 500 degree, because there is the changing from austenite to bainite, ferrite, or martensite. And normally with the laser beam, you are in the thick plate area round about 2 or 3 seconds, and that's a little bit too low or too less to get good hardness values and good toughness values. So maybe you should increase it, but you cannot increase only by the welding parameters. You can increase it with preheating, but no one wants to do preheating.
Yeah.
And the other thing is, the thicker the sheet metal, the slower the welding must be. As the higher mass of the component dissipates the welding heat more quickly. We change there from a 2-dimensional to a 3-dimensional heat dissipation, and that means the hardness is much higher if the plate thickness is higher. And now to say what is standard, high experienced companies are able to optimize the production that 15 millimeter can be welded in a single layer. That's maybe Meyerwerft. The state of the art assumes 12 millimeter. So if you can bring your laser into 12 millimeter plate thickness with a perfect root, perfect surface, defect-free, good values, then you have a very good start. So maybe you should start with not with the very thick plates, but with thinner plates. I am working for you in this part, but also for you, maybe go down with your plate thickness and to make it 100% perfect. These are some things we made for shipyard. This is hybrid welding. This is not only single laser beam welding, it's hybrid welding. On 18 millimeter thick plates we developed. And here on the next slide, you can see it a little bit bigger, there is a root, very nice root, well formed, no undercuts, and here the X-ray, and here now X-ray, it's on the other way. So porosity or cracks are white, and you can see here's nothing. Okay. Coming now to this presentation I made on Lane last year. This we have done. It's primed plates, and yeah, I will go maybe one look into the lab. So the laser is above. We have 3 meter on focal distance, and yeah, the shapes are these ones: the point, the circle, boomerang top, boomerang bottom, with different frequencies, and we kept the welding speed to 1.2 meter per minute, adjust the power for a good route, and we made visual inspection and cross sections. And visual inspections, I made this cross section, and I measured the width of the weld, the width of the root, the width of the middle, distance from surface to 3. So where is this smallest part in the weld, the root excess penetration, and the weld underfill. And so these are some thoughts about it. I think we should go directly into the results. One thing was that the plume here influence the root formation. You can see here. So you have to solve it that you have always the same conditions. But after a few days, we found the right setup to make really good welds with different different surfaces and roots, all for 10 kilowatt at a frequency of 100 hertz. And if we increase the frequency, then we have changes, nice changes. And these are the cross sections for that. On the left side, always 100 hertz, and on the right side, the 100 kilohertz. And there you can see the differences. And regarding the standard 3919 quality level B, we have only 3 welds which fulfill it because of the root excess penetration and the weld underfill. And for 8 millimeter, we have a underfill which is possible of 0.5 millimeter and a root excess penetration of 1.4 millimeter. And only one. The green one, it's the point. It's a circle at 100 kilohertz, and the boomerang bottom at 100 kilohertz fulfill these requirements. And yeah, so I will go to it. What was different, or maybe I will go back. Here you can see it very clearly. What you also can see here is that we have again, not the right mirror shape of the fusion line. You can see it at all the things. And yeah, it's one moment. Ist irgendwas? Okay. And it's not mirror-like. We know the reason for that. I will come to that later. Yeah. And yeah, so we change the melt flow. You can see here the ending crater from the point shape and the boomerang bottom at 100 kilohertz. And what you can see here is that these ending craters completely different, longer, and this leads to a different technical mechanical properties, I think. Unfortunately, I'm not sure if this is good or bad. So we are testing in the project we do together. But a friend of mine gave me here, Richard Banashik said, with the boomerang bottom, there is definitely less martensite, lower bainate in the weld metal. And yeah, so that means we changed the cooling time a little bit, and we maybe we interrupt some things by solidification. We are not pretty sure what happens there, but yeah, on the right side, you can see that my welds are much wider than your welds. And this is important for production, because if you are too small, then you get problems if you have deviation in your machine.
Yeah.
And this is the reason why I use this really big focal length. I'm not sure if the mechanical properties are good or not. We are testing in the project we do together. Regarding distortion, the boomerang bottom is better because the shrinkage is only so the shrinkage on the surface and on the bottom is nearly the same. For the point shape, there is big shrinkage on the surface and less shrinkage on the bottom. And yeah, that leads to higher distortion. Okay. Yeah, and what we also saw is if we increase the frequency for the circle and for the boomerang top, I think, yeah, so we have a crack there. It's so funny. In the next slide, I'm not pretty sure if it is a really hot crack. So I think it's really a hot crack with segregations, because all the things fit together if you see there.
Yeah,
and it's not a shrinkage cavity, I would say. But why? I don't know. But we are on the beginning of all the things. Coming now to the not mirror-like shape of the weld. It was a scanning mirror, or the scanner, which tilts the beam by 15 or 17 degrees. And that was the reason why we put this vacuum chamber in this angle to get rid of that. And now we skipped the scanner and weld without the scanner. And my colleague told me that he needs less 1 kilowatt less power to get the same results. So the scanner sucks round about 1 kilowatt at 12.
Depends on something like that. I don't remember exactly, but here when they calibrated the system in integration and then they put on the scanner to make sure that everything is fine, they do need to recalibrate the power levels as well.
Yeah.
So it does absorb some.
Yeah. So I will not use a scanner for thick plate welding because I need to trust the system and the scanner. I think for partial penetration is okay, but for thick plate weldings with good roots, we need more safety regarding focus shift. And at the moment, I cannot say that this scanner is good for thick plate welding.
But is this shift, this angle is related to the crack that you saw in slide 27, or it's like two different phenomena? No. They are not correlated.
No. That's different. That's different.
Okay.
So this is these are some trials with laser and vacuum with Civan laser. The comparison between the things. This is the dot. What you can see here, or generally, you have a very high tendency to spiking. We will see at lower frequency that there is also spiking everywhere, but if we have higher frequency, then it gets better. And here the comparison on the right side, 1.2 meter per minute at 10 millibar in comparison with the 8 millimeter shipbuilding steel. Here is what I mentioned before, that at lower frequencies we have the spiking. And so at lower, you can see the spiking there with sometimes with porosity, and for the higher welding speed we have shrinkage cavities, but this we can avoid with adaptation of the shape. I think it's not so really critical at the moment. And this one is my favorite on the right side, from the shape, and so here for laser, the laser fits really good. So I don't want to repeat everything, but this I want to show you. This is 25 millimeter thick plate, and this is done in one run with laser beam submerged arc hybrid welding and additional electromagnetic backing. And this I try to bring into industry, and I would say this is ready for thick plate area, and with these results you can convince thick plate manufacturer to use lasers in fabrication.
Mainly because of the root.
Yes,
right?
Because of the root. I think the root is the most important
key
thing.
Yeah.
And on that we have to work to understand why we cannot control. Maybe we need simulation to understand what happens there. We are working on this topic. For simulation, we use a new simulation tool for the hydrodynamics in the capillary and around. It's called SPH, Smart Particle Hydrodynamics. It's a simulation software, and I prepare a proposal for Deutsche Forschungsgemeinschaft to do this simulation program and to understand how we can control the root without dropping and forming a good excess penetration. So they need an excess penetration on the root and not an undercut.
And can you apply the Civan laser in your simulations with this software?
For sure.
Okay.
That's a new thing. That's a new shit, you know. So I will skip the presentation. Then I see you again. Hello.
Hi.
Do you have questions to my presentation, to my thoughts, to my results? Everybody is speechless.
Yeah, well, I asked everything I had during your presentation. So.
Okay.
Alexei, anything?
What do you think about my welds, Alexei? Be honest.
Some of them looks great. So, I understood we need to work on the road to focus on this, because before we tried to achieve highest penetration, this lowest power, but it was bad for root quality. Because when we use our sequence, I'm using 1 point, this some dynamic beam shape, it's create a sharp root and even on partial penetration, you can see it's